In this video, we're going to find I1 using the node voltage method. So when we look at this, we know we're going to be finding the current I1, which is the current through this 6K resistor, right? So because we're using the node voltage method, the very first thing we're going to do is identify all of our essential nodes. We know this is an essential node. I'm going to call it 1. This is an essential node. I'm going to call it 2. And we know at the bottom here we have our third essential node, but I'm just going to take it as the ground node. Now, because we're finding the voltage at each of these nodes, I'm just going to write V1 and V2. So let's begin. We're going to write a node voltage equation at node 1. Right? So we know this is node 1. We're going to assume the current is going to go in this direction. So it's going to leave the node. So when you write down that current, we're going to have V1 minus 3 divided by 6,000 plus, we're going to assume the current is going to flow in this direction. So we're going to have V1 over 12,000 plus, we're going to assume the current is now going to flow in this direction. Now when we look at this, something interesting is happening here. We have a voltage source in between two nodes, right? And because we have this voltage source in between two nodes, it's important for us to recognize if we know the voltages in any of those nodes. Well, we don't know the voltage at node 1. And when we look at V2 now, which is the voltage at node 2, we don't know the voltage at node 2 right away, which means we have a special case which we are going to be calling the supernode. So in reality, because we have a voltage source in between two nodes that we don't know the voltage for, we always must use the supernode method. So we're going to ignore this voltage source for now, and we're just going to write the node voltage equation for node 2. In the same equation, we was writing the node voltage for node 1. So we're going to have the current flowing in this direction and the current flowing in this direction. So we're going to have V2 over this resistor, which is 6,000, plus the current flowing in this direction is going to be V2 minus, but pay close attention to the polarity of this voltage source. You see that? We're going to enter the negative terminal if we walk from this way. So this is going to be a negative voltage. So we're going to say V2 minus 3 divided by 12,000, and all of that equals 0. So we can start to simplify this. We know the LCD is going to be 12,000, so we're going to multiply each term by 12,000. When we multiply the first term by 12,000, we're going to get 2 V1 minus 3 plus, when we multiply the second term by 12,000, we're just going to be left with V1 plus, when we multiply the third term by the LCD 12,000, we're going to get 2 V2 plus, when we multiply our last term by 12,000, we're just going to be left with V2 plus 3 equals 0. Okay? Now let's start to simplify this. This is going to give us 2V1 minus 6 plus V1 plus 2V2 plus V2 plus 3 equals 0. So when we start to simplify this further, we're going to get 3V1 plus 3V2 equals positive 3. So this is going to be the node voltage equation at that supernode, and this is going to be equation 1 for us. So this is equation 1. So instead of writing node voltage at node 1, this was actually node voltage at supernode. So when we wrote the node voltage equation at the supernode, we just ignored this voltage source. Now we have to write a constraint equation due to this supernode method. And that constraint equation is going to involve those two nodes that is going to connect that voltage source. So we know we're going to have node 1 and node 2, and this is the source, which is a 6-volt source. Because of the polarity of this voltage source, when we write our equation, we're going to write it as V2 minus V1. And the reason why we're going to do that is because the positive terminal is connected to node 2. Therefore, we're going to say that node 2 has a higher potential or a higher voltage than node 1. So when we write our constraint equation now, we're going to write the voltage at node 2 first minus the voltage at node 1, and that's going to equal 6 volts. So for our constraint equation, we're going to have V2 minus V1 equals 6. So this is going to be our second equation. Now when we look at this, we needed 2 equations because we had 2 nodes we were supposed to find the node voltage equations for. Now when we look at our 2 equations, we have the same unknowns, which means we can solve this using systems of equations. So I'm just going to use the matrix method, right? If you want to use simultaneous equations, you can. I know the unknowns is going to be V1 and V2. I'm just going to rearrange this equation to be negative V1 plus V2 equals 6. Okay? So we know for our first equation, we have a positive 3 V1. So I'm going to write positive 3. Then we have a positive 3 V2. Then that equals 3, positive 3. Now for V2, we have a negative 1, right? We have a negative 1. Then we have a positive 1 for V2, and that equals 6. So we're just going to use our calculators now and take the inverse of A and multiply it by B. When we do that, that's going to give us V1 equals negative 2.5 volts. V2 equals positive 3.5 volts. So these 2 voltages is going to be the voltage at node 1. So we know the voltage at node 1 is going to be negative 2.5 volts. The voltage at node 2 is going to be 3.5 volts. I'm just going to circle it. Okay. Now that we know the voltages at each node, we're just going to now look to see what the question wanted us to find. They want us to find the current I1, which is the current flowing through this 6K resistor here. So to find this current I1, it's very important that we can see the voltage at node 2 is the same voltage across this 6K resistor. We just found the voltage at node 2, which means we can just use Ohm's law to find the current I1. Therefore, we know I1 equals V over R. We know we're going to be using the voltage at node 2 that we just found, so we can write it as V2 over R. Therefore, we can say I1 equals V2 equals 3.5 divided by the resistance, which is going to be 6K. So we have 6,000. Therefore, when you put this in your calculator, the current I1 equals 0.58 milliamps. So this is going to be the current flowing through that 6K resistor, and this is going to be your answer, 0.58 milliamps. So we've successfully solved this problem, and this problem involved a supernode, but as you can see, anytime you have a voltage source in between 2 nodes that we do not know the voltage for, we're always going to have to use the supernode method. It's not hard, as you can see. Stay tuned, let's work some more examples.